I'm going to introduce our next team, and they're actually a French research engineers from France. Is that correct?
That's it.
And they are going to give us an interesting presentation on Martian rover for human exploration. Take it away, guys.
Yeah, we have a small, our rover is called Remus, and we have a small Remus there. We can take and have a look at it while we're doing the presentation.
Pass it around.
Yeah.
Can you talk a little louder, please? Here you
Yeah.
go.
Okay, thank you for being here. My name is Charly, and we're a group of 5 students from France. We are studying aerospace engineering at Dezprez, which is a French engineering school in Paris. This year we had the opportunity to work in a station with Planet Mars, which is the French division of the Mars Society. And our project was to design and engineer a rover for the main exploration of Mars. So we are here to present you the results of this study and to discuss about it from an engineering point of view. So let's start. First, we have to characterize the environment in which our rover will evolve. So, as you know, Mars is very hostile, and it will cause a lot of technical issues that need to be dealt with to engineer our rover. So here we can see a quick review of the difference between Earth and Mars, and the characteristics of the Mars soil will define the first framework to start the study. But more importantly, there is no help on Mars, so we have to design something highly resilient and as self-sufficient as possible during all the mission.
So about the specifications, we have a range of actions of about 200 kilometers. We wanted our rover to have a mass under 8 tons, an autonomy over 15 days, an all-round rover, and 2 passengers in the nominal mode, but most importantly, up to 6 passengers in case of emergency. We wanted it to be pressurized, and we chose 0.5 bars, and an overlapped conception, redundant and robust.
So let's talk about of the propulsion unit and the way to make our rover moving. So for the wheel architecture, we have to look at what have been tested for space exploration. We have 2 models: a solid wheel used for opportunity and curiosity, and a deformable wheel used for the lunar roving vehicle. So due to the steep terrain, we have selected a deformable architecture with a mesh of shape memory material. The rover will have 6 wheels for stability, and for the energy, we have chosen an electric propulsion, and the fuel would be too complicated in terms of mass and reliability. So now we have a simplified architecture of the power unit, of the propulsion unit, so you can calculate the different needed of the rover, the power and the energy that should be provided. For that, we have taken a rolling cycle, which is used to determine the typical accelerations and decelerations of a vehicle. So now we have acceleration and deceleration, and we can calculate the instantaneous power that should be provided. And by integrating that power, we can calculate the energy for all emission, which is about 400 kilometers. So for that, we have simulated an ascending rate of 20% to simulate the worst case. We have calculated that we need 970 kilowatt-hour for emission over 400 kilometers, and this value will be implemented in the computation to find the mass of battery need. The second step was to simulate the propulsion unit under various conditions and failures to ensure that we have enough power to operate at extreme conditions and to be fail-ups, fail-ups. So as we have seen, to compute the problem on the software permits us to have a global vision of the propulsion unit and to test the system under various conditions.
All right, thank you, Fred. My name is François, and I'm going to present you the life support system. So, when we talk about sending people on another planet, the question of every moment is how do we make them survive and give them the best work conditions? Our rover isn't an exception. Solutions have to be found for each question if problems this question generates. The life support systems has to be robust, efficient, easy to maintain, and capable of facing any emergency. They also have to fit in the limited room offered by the rover, and use a minimum of energy because the power of that kind of vehicle is obviously limited. The solutions we came to find are based on existing technologies, like some of them are already used in some space vehicles, like the ISS or the space shuttle. We also use some speculation from other specialized studios about the increasing performances on some devices or young technologies, especially about electrical devices consumption concerning the life support systems. So there's many problematics about living somewhere out of Earth. Of course, we have to eat and drink, keep a breathable atmosphere and control its moisture and temperatures to work in good conditions. We also have to protect ourselves from external threats, and we have to deal with our waste. Most of the water used in the mission is kept and could be recycled when the rover came back to the main base, because the water recycling system on the rover would be too big and use too much energy. This is why all the systems have to run in closed circuits. The best example for this is the interconnection between the air revitalization systems and the water systems, especially about the CO2 absorber, which use the wasted water to run, and also participate from the internal temperature. So, an interplanetary mission would be fun without some failures or device breakdown. So, one of the most important characteristics of all the life support systems is that they have to be fail-fast. That means that if there are failures, they have to keep working. For example, the CO2 scrubber system is using absorbent cartridges, which are like very simple utilization, and they can be brought in good quantity. The EVA room presents a lot of advantages. It is separated from the cabins by a reinforced door, and it is obviously easily pressurizable because of the EVA conditioning. And so it can provide a refuge for the astronauts in case of slow cabin depressurization, but also in the case of high solar radiations, we're gonna speak about this later in the presentation. The access to the suit is quite simple too, to permit a quick EVA in case of the need to repair something from the outside. Finally, the life support systems have to take the less room as possible to allow the astronauts to live in a decent place for 2 weeks, a place where they can lay down, cook in a real kitchen, and have room enough for the scientific work and sample collecting.
Hi. Hi.
No.
You don't have to be close to it. Okay. Perfect. So now we're going to see how to provide the rover the good amount of energy to enable it to deal with all the tasks it's been designed to deal with. So we had to provide energy from vital system, which is obvious, especially in the hard atmosphere of Mars. For the 6 wheels engine, which have to enable our rover to reach the 400 kilometer needed. And also for the scientific equipment that will be on board for an exploration mission on Mars. All in all, we took a 20% margin to be really safe about all the energy supplied, and we reached a total amount of 1,800 kilowatt. So at first, the idea was to be totally independent on the production of energy. So we first turned to the solar energy with the multi-junction solar panels. It's a technology developed by aerospace engineers. It's quite the same system as solar panels, but it's far more efficient because it's composed of different layers. Each layer is absorbing a sun wavelength, and so it's duplicating its efficiency. It can reach 65% efficiency for 3 layers. And so if we cover all Remus's roof with those panels, we can generate 510 kilowatt, which is a lot, but really not enough. So we had to turn to other energies. So then we thought about thermic energy, but it has a high reliability. It's been used in many probes program, some very famous one, as you can see, but it was not producing enough energy. So we turned to another system, which is a state-of-the-art system developed by NASA, and it's producing a lot of energy for really enough for a rover. But there were other problems. It's very large. It was very, very heavy, and more than all, there are some very important health risks because it's using nuclear fission, such as in a nuclear reactor, and it's producing gamma rays, which are very dangerous for the human body. At this point, our project, it was clear that we couldn't be self-sufficient in energy, and we had to find a way to stock it. So among all the different systems that are existing, the two best ones, the two most adapted ones were the lithium-ion batteries and supercapacitor. The second one has a better, a more adapted charging temperature for Mars atmosphere, so it was quite good. But the first one has a very, very high reliability because it's been used in many fields on Earth, and we know how it's reacting. So we chose this one. We did a simulation on MATLAB to estimate, thanks to the past decade's evolution, what would be the capacities in 2040, which is the date of our rover, when our rover will be producing. So we decided to have 4 batteries that will be fixed on the frame of our rover. Each battery would be 310 kilograms and have a volume of 0.34 cubic meters. There's another system which is here, the structural batteries, but it's very new, and so we don't really know how to adapt it yet, but maybe in a few decades it would be a better solution for this kind of rovers.
Hey everyone, I'm Pierre. So we will talk about the structure, and there is a few critical points that are obvious at first we have to deal with. To begin with, there is the thermal resistance, the mechanical resistance, and the radiation protection. But there is also a few other points we have to deal with. We don't want our rover to burn in 2 minutes, obviously. We want it to be lightweight. As I said in the specification earlier, we want it to be under 8 tons. And one of the critical points is to support cycling, the periodic change of temperature between the day and the night, which has a great impact on materials, in fact. So that's why we chose a sandwich structure, so composed of few layers of materials. And what will compose this structure, this sandwich, this structural sandwich? Well, to begin with, there is the carbon epoxy, the T6035. It's shocks absorber. It has the lowest thermal expansion coefficient among carbon epoxy in general, based on a study from the NASA in the 90s. I don't know if you heard about the PLR, which were pressurized lunar rover, and they chose this exact reference. And it also has the lowest density among the carbon epoxy. On top of that, we have the honeycomb structure, so it has great mechanical properties. It is used in few spacecraft missions like Mariner 3, for example, and few rockets. It has great thermal resistance. It's lightweight because it's aluminum, so we chose this structure on top of the carbon epoxy. To cover it, because as you saw, it's plenty of holes, we have to put another layer of carbon epoxy just for the redundancy. Over that, we have the MLI. You may know it with probes because it's usually used in probes. The thing is, it's really fragile. First of all, it's fragile because of the Martian environment with micrometeorites. So on top of that, we have a thin sheet of aluminum, which will protect from the Martian environment. But there is also a problem because the MLI is not expanding because of temperature, which is not the case of the carbon epoxy. So we had to put something between the two. What we chose is polymeric EPDM elastomer. It is used in the automotive industry. It's leak-proof, and it has a great range of temperature, which is great for the Martian environment. So the MLI on top. About the radiative events, well, we want to protect the humans on our rover, so we decided to, in the SAS, to put a shield, a boric polyethylene shield. It is great, but because it is used in the nuclear fields and medical fields to protect from rays and solar rays in particular, in this case. But nevertheless, drawback, it's really heavy. And the thing is, the polyethylene boric shield is 1/3 of the total mass of structure, even if it's just in the SAS. So as you can see here on the table, the total mass is 1,600 kilograms, and you can see the different thickness of our materials.
Hi, I'm Charly, and I'm going to present you our strategy to design the mechanical part of the rover. Firstly, we check all the technologies already existing or which will evolve in the same environment. Our rover will evolve in the Martian desert, will be the size of a small motorhome. So we took example of the trucks that participate to the Paris-Dakar race. The technology used on those trucks have been used on the field, and as consequence are very reliable. This feedback was very useful for the design for the strong frame of the strong frame. We did also reverse engineering on the existing rover to understand the main specification. And we are also inspired by the movie The Martian. Indeed, in the later, the rover has a very large canopy, which is something very interesting because the rover will evolve in a hollow territory. And so to have a very large visibility will allow the rover to avoid a lot of troubles. And if the astronaut wants to check the ground, then can do that being inside the rover. Now, 2 words about the general shape. When we designed the living area, we relied on the value of the specification, general dimension, differential pressure, shielding, and after some material resistance calculation, we found that the most optimized form in order to resist to the pressure was the cylinder. But at this point, we had to take a step back and must think about the following projects: the layout and economics for astronauts. One of the most economic forms is the cube, but it is in the meantime in the worst form to resist to the pressure. So we had to do a compromise, and we opted for an hexagonal shape. In order to optimize the mass of the rover, we did some finite element calculation, and with the calculation we saw that the upper part of the structure was the most fragile. So to solve that trouble, we put some stiffeners. It was crucial for us to have a global vision on the specification, to think about the whole system. And nowadays, we can use some state-of-the-art computer tools, enabling us to save time and optimize our design. Designing with CAD software allows us to have 3D vision and also to use finite element calculation softwares. But regarding the payload capacity of the rocket, we knew that we'll use composite materials. However, they are very hard to model in finite elements, so we did another compromise. We chose to use a very mature technology, the aluminum. Here, an example, we take an example of the frame. To optimize the mass of the rover, we iterated the frame. With the finite element calculation, we spot the critical points, and we drilled and scoop out all the rest Here, the first iteration. Here, the third iteration.
So we just few of those different steps and problematics we met to design a Martian pressurized rover. It appears that each part are very linked and influence each other, especially about the massic and electrical balance. The results we found are compromises we made with the different solutions we have in our hands. It was a real pleasure to do this project because it covers a lot of different fields outside the only aerospace engineering. We want to thank all our partners, and especially Richard Heinemann, who is just here, for helping us for this project and to permit us to be here today, which is the best achievement, I guess, we could have for this project. Thank you for your attention, and don't hesitate to ask all the questions you want. All right, so please, sir.
What portion of the atmosphere do you have it pressurized to?
Sorry?
What is the differential pressure of the cabin?
It is, so the cabin is pressurized at 0.5 bars, and so the difference, the pressure between the cabins.
Yeah, how many atmospheres?
So 0.3.
0.5?
So 0.5 atmosphere. Yeah.
Thank you.
No problem. Yeah.
Question about the propulsion. Did you look at and reject a methane engine, given that methane seems to be relatively easy to make on Mars, and why? And also for the battery system, are you planning to heat it, or how are you dealing with the reduced discharge rate at very low temperatures?
Good question.
For the battery, we think about to cover it and to make it thermal proof. So we have closed atmosphere also for the battery.
Did you look at and reject a methane-powered engine for the rover?
Unmarked fuel would have been too complicated in terms of mass, and if there is some leak or something like that, it would be too complicated. And we want to have only one source of power for the rover, so we have selected electric propulsion.
So are the solar panels still on the roof or not? There are roof-based solar panels to charge the batteries?
Yeah.
How much range do you anticipate you can gain in a single day only charging off of the panels?
It's 500 for 15 days, so it might be 75, about 75 per day.
75 kilometers a day?
Not a.
We didn't consider the distance per day. We just consider all the mission, which is about 400 kilometers for 2 weeks, but not distance per day. So we have estimated that solar panel can have a gain of 15% of the total energy of the rover.
And where does the rest of the power come from?
For the battery.
Where do the batteries get their power?
We are considering that there's a basement, like a settlement, and our rover is just for a 15 days mission, but then the crew goes back to the settlement, and in the settlement there might be a kilopower used. That's why it was easy to charge and to have electricity.
Okay, then why do you need the solar panels at all?
To not to have to make the batteries.
For safety purpose and to have reliability on the road. If there are
There's a problem on
problem on the rover, there are still the solar panels.
The mirrors on the side, are those radiators, heat radiators?
Sorry? This one?
Yeah.
Oh, that's on the price of the wheel, yes.
Yeah.
Oh, that's just reflection?
Yeah.
Oh, okay.
The manipulation.
Oh, yeah.
What was the question?
Did maybe you referred to this earlier? Did you consider using like just hydrogen oxygen fuel cells to power the?
It's the same problem than methane.
Methane.
Yeah. We don't want to have
Sure. My name rhymes with Hindenburg, so I know. So you consider it would be too hazardous to have a hydrogen oxygen system? Okay. Have you run thermal calculations, your heat loss at night, for example?
No, that's the continuity of this project from a group of three Charlymen will be in charge of the exact calculation of the depollution and the loss of.
Yeah, because it wasn't in your energy budget.
No, there is just a basic calculation like the total with the sandwich structure. We have the thermal loss, but the basic one. We didn't consider everything, and that's it will be the next step and the next step of the project.
Got a insulation design that might work.
You're storing your transportation energy, your mobile energy. That gives you a point of no return. In other words, a distance like aircraft, where they're not going to go home again because they don't have enough fuel to get there. So you have to plan that.
Actually,
The range of the mission is 200 kilometers, so we have calculated that the maximum distance of the base will be 200 kilometers, and we have taken a lot of margin for the engine.
and so actually the power supply is designed to be like 400 kilometers, to have like 200 kilometers forward and then 200 kilometers on the other side.
Would make more sense to stay at a radius so you can get home.
Yes.
Yes.
They're not going to take risks, I guess, in the case of that kind of mission. If they see there is just one problem, they have to come back, and so systems are fail-ups, so they can come back. When they see their problem, they will automatically come back.
Two questions. First, were you envisioning this rover to be delivered intact to Mars or be assembled there? And second, what kind of terrain is it designed for? So what kind of inhomogeneities in the terrain can it handle?
For the first question, the rover will be on Mars complete because we think, for example, the Starship, we can launch a rover like this. It's a supposition, but we take this hypothesis. And for the question,
it was considered at first that we will be able to bring this rover just not with parts of it, but currently there is no technologies. No rockets able to bring in. Like it's really massive. 8 tons, 3 meters in diameters. So for the moment, nothing can bring him to Mars. But we are supposing that it will be 2040. So we hope something will be able to bring it.
And we guess it's going to be. And your second question was?
For the terrain, what kind of terrain can it navigate?
Actually,
Well, the maximum slope is 28 degrees, I think, and the wheels are 1.20 meters diameter, so it can climb little rocks on the surface.
Yeah, have you thought about putting little windows on the side there for the astronauts in the science in the back?
No, we didn't, because of the solar
on the
panel.
side?
No, actually on the side.
Okay. Actually, no, we didn't do that because of.
Oh, it's only designed for 2 astronauts?
Yeah, so that's not in nominal mode.
Nominal mode, and
How many?
6 in emergency mode. It can carry 6
6 in the module? It could carry up to 6 though.
Yeah, up to 6 if it's in emergency. Like for your scientific mission, it would be just 2, the nominal one.
That's why I was asking about the windows on the side if you're going to put some. You might?
perhaps.
I mean, it could be possible, but when you're an engineering, you don't want to put windows on the side.
Pressure.
Yeah, for the mechanical properties.
Yes, you considered, you discussed the heat problem, that you had to kind of leave that aside. One of the interesting things in the movie Martian was he used an RTG basically, not for power, but just to keep him warm. And it would also provide a backup, power to just support minimal an emergency. Say you have 6 people in there. The main base got hit with a big meteorite or something, and you're just sitting there waiting for rescue. It would be nice to have an RTG so you can keep the radio operating and keep warm.
It's a possibility to put another on the previous to put like a side rubber, like just a small part to bring with the rubber, but apart, not linked to the pressurized habitat.
Oh, okay. Yes, so it could have it in thermal contact inside the atmosphere.
So why not? We didn't consider
that would be a nice backup.
Yeah.
Thank you for the day.
It's just a quick question. Can you drive this in extreme environments like snow, deep snow, and also have you considered like if you've got solar panels, right? If there is no sun, like for example, I just deployed a mission to 15,000 feet in Nepal, and it was monsoon season. It rained like crazy, and there was no sun. We couldn't use any of our solar power generators.
In that case, we just have the batteries, which are providing like more than the 2/3 of what we need. And in case, the crew can try to deal with its resources. And if they can't use the solar panels, they will shorten the mission.
For the terrain, we didn't test on snow or other surface. We just test on the regolith, and we take the friction coefficient of the regolith to have the different calculation for the power that should be provided by the regolith.
And on top of that, I guess there will be like meteor prediction around the settlement. And so I guess they will not plan a mission, like a nominal mission, exploration mission, if like they know that the weather will be absolutely bad, I guess.
Unless it's a global dust storm. The irradiance reduction. The irradiance
hit your base, then there's a global dust.
The irradiance reduction during a typical dust storm is not significant. So.
Just go ahead. One final question. If you're off and you have an emergent condition, you would be stranded for like 14 days or something like that. How much did you account for food and water for that duration?
So about the food, actually, you can take quite a lot of food. If you take only what's the word? Localized food. Dry. Thank you. So you can take a lot of this, and but the real problem is about water, actually. So the water can support the 2x quite easily, and we have enough. We planned enough room, water room, and took 30% margin. But I guess if it's the mission's prolonging, they have to make choice about how to use this water. I guess they can leave. I can't say the exact number of days, but 10 days more perhaps with 20% margin.
We took margin everywhere to be sure that.
Yeah.
I was just thinking that if you had an ice container on top and sides, you'd also gain the radiation protection.
Yeah, it was one of the considerations.
Thank you, everybody.